Hello, and welcome to Game Revolutions, the series where I take a video game that I started writing in high school and see if I can improve it now, with all of the knowledge that I have gained since then. Why? Why am I doing this? Because everybody knows writing games for the Coco is the quickest way to earn enough money to afford a Ferrari. I had removed game elements so I could focus on double buffering and stack blasting and getting the scrolling speed nice and fast and smooth. And in the last episode, I added back joystick support to slide the car left and right. But in so doing, I ran into a performance issue where the scrolling speed would stay fast and then go slow and then go fast and then go slow. And I was left wondering what was going on. In this episode, I'm going to walk you through step-by-step my performance investigation to figure out what's going on, narrowing down the cause, and pinpointing the ultimate thing that needs fixing. No spoilers, but if you're curious to know what the ultimate cause was, I'll give you this hint. If you're really into deep technical content, you're gonna have a blast. This is where we left off last time. If you take a look at maybe the mountains to make it most obvious, it goes slow, then speeds up, and then slow, and then speeds up and slow, and then speeds up and slow. And why? That is what we need to investigate. So the very first thing I tried was to suspect the new code. And I looked through the new code that I added, and the first suspicion is that the joystick routine in the ROM, it's a nice compact bit of code, but it is kind of lengthy and it does do a lot of things and it's got some loops in it. And so I asked myself, well, if I just commented just that out, what would the result be? I called the joystick routine from the ROM at the very top of the copy car routine. So this is going to tell me what the joystick is doing. The easiest thing is just comment that out. The rest of this will still function fine. I'm still going to read from that memory location at row 2 what the value of the axis is, and fine, so it's not going to be correct, but who cares? The main thing is to see what happens with the scrolling speed. So let's just make that one little change and see what we get. And it's fixed. Everything is going fast. So at first blush, it looks like that thing is to blame. But why would it be so inconsistent, and why would it be so consistent in its inconsistency? And what I mean by that is, why would it slow things down, speed them up, slow things down, speed them up, and do that to a rhythm? So it's not always slowing things down, but it is doing so with some kind of a regularity. And a quick scan through Unraveled and the source code for that Joy-In ROM routine does not make it obvious that it should do that. So I decided I need to get a little bit more data, more than just my eyes can show me. So as I've done before, I'm going to go into MAME, and I'm going to set a breakpoint just before the sync at the end of the main loop. I don't really need to set a breakpoint after the sync. I know what this is going to show me. It's going to show me that we're at the V blank. The question is, how far down the screen did I get to just before the sync? And that gives me a rough idea of how much time my main loop takes. So I'm going to add back the joystick routine. So we have the slow down and the speed up, and I'm going to set this breakpoint and take a look. So you can see we're back to the speed up, the slow down, the speed up, the slow down, the speed up, the slow down. So I'm going to set that breakpoint, 3E79, And we're right here. So we're all the way down to 221. Beam Y, we're down to 221. Let's see how consistent that is. 222, 221, pretty consistent. Now it's 213. Back to 221, 221, 221, 221, 222, 199. Okay. 200. All right, that's pretty different. That's a good 23 less. So we're now in the low 200s. Whoa, was that a 147 I saw? Now we're in the 210s. The 210s. I'm just going to hold this down and keep my eye there. We seem to oscillate mainly between 220 something and 200 something. So there's some kind of rhythmic change. And the question is, am I still going to see that rhythmic change after I comment out that get joy routine? First of all, at this point, we'll see that there's no rhythmic change visible. So MAME is showing me what XROR was showing me, which is that it seems okay when I comment out the joy in routine. Let's set that breakpoint. So beam Y is 180, 179, 179. So pretty consistently around 180. Oh, 114, 120, 180, 180, 180, 190, 190, 179, 180, the 80s. We seem to go somewhere between the 70s, mostly between the 70s somethings and the up to the 90 somethings. So there's still quite a variance. There's a good variance of maybe 20 scan lines, even with that commented out. And that's telling me that adding the extra time to do the joystick routine pushed us over the boundary of a full frame's worth of work that we're doing in one go through the loop. So there was still a variance. There's still something that's inconsistently yet consistently changing the speed in waves. And when I added something that was consistently slow, like the get joy routine, that pushed us over the boundary when we were in the slow area. And by pushing us over the boundary, we lost a frame, and we would lose a frame consistently for a second or two back until we were then going every frame. So that allowed us to visually see that there was a problem, but there was a problem even before the joystick routine. So now the question is, how do I find this weird, inconsistent change? Well, one of the culprits that came to mind immediately, even though this didn't seem very likely, is the mountains. I had a little comment that allows me to make the mountains move all the time rather than every 3 frames. And I was just wondering, I would like every go through the loop to try to be as similar as possible to every other go. And this is an intentional change in performance every 3 frames. Now, the issue that I'm seeing lasts a lot longer than 1 frame every 3 frames. And it happens a lot less often than every 3 frames. But still, I just wanted to do this and check on those numbers and see. All right, so now you can see kind of how fast everything goes when the mountains and the ground is moving. And since the joystick routine is still commented out, it's still quite fast all the time. But let's set that breakpoint. It's now at 3E77. So here we are right before that sync. The beam Y is 114, 184. I'm not going to count that first point. Okay, so it went down to 70-something, now up to 90-something. 90-something down to 70-something. There's a 114 in there. I'm not sure what that is. But most of the time, we seem to be varying still around 20 scan lines. So as expected, The mountains are not responsible. But it's good to eliminate the things that might maybe be responsible, just to make sure that they're not. And so now we can, with a clear mind, start looking at the code and figuring this out. The main loop starts here. We're doing some buffer swapping. This is the real meat. This is where we're doing all of the stack blasting, all of the drawing, now the copy car, and then a bunch of stuff I still haven't brought back. These are updating variables that are used in the stack blasting for the next iteration, and then we're at the bottom. So really the meat is here, and we can use a technique kind of like binary search to try to figure out what's responsible. So if I comment out, say, half of these things, and then I ask, all right, am I still getting a problem? Is there still an inconsistency? Then I know the problem is here. If I'm not, then I know the problem was here. And in either case, I take the half where the problem was, and I comment out half of that. And then I just keep on like narrowing down until I hit the area of the code that must be responsible. I went through that exercise, and it may be no big surprise, but the responsible code was the extremely complicated stack blasting code that I went over a few videos ago. It's called both when I'm rotating the mountains or buildings in the background, and it's called when I'm rotating that top line of the ground. It's using the same routine. This is more pronounced because there's a much larger region of screen that's being used to rotate the mountains or buildings. So I kind of started to focus in on here. It set up some variables and it called draw rotated region. Draw rotated region is basically a helper that calls copy rectangle twice. Here's a refresher of what's going on, because this is extremely complicated and I myself forgot most of the details, so I think a review might help. What you see up here is what the data for the mountains looks like inside the code before it's stack blasted. So it is upside down and backwards and partially unreversed so that it is ready for stack blasting. It's divided into 4 groups. Each group consists of 8 bytes, so I call each of these groups an octet of bytes. The groups are in reverse order. So the group all the way on the right is responsible for the left octet of mountain bytes. The next group is for the next one over. The next is the next, and finally the leftmost group up here will become the rightmost group of bytes when it gets blasted. But of course it's more complicated than that, because within each group the bytes are not reversed. The bytes are actually in order. That means the first byte that should go on the left-hand corner is actually the first byte of the last octet. And then we go to the second byte of the last octet, and then the third and the fourth, fifth, sixth, seventh, eighth. And then when we're done with this octet, we rewind back to the previous octet, starting at the beginning and then moving forward. The reason this is so crazy complicated is because I needed to store things in a way where I could grab from any offset the starting point. Since the mountains scroll, I'm not always starting with this at the leftmost part. Instead, I need to be able to start anywhere, and from there start blasting, and then have it appear like the mountains had rotated from the last frame. So when we first start, this is where we start our blasting, and the way we do it is we divide it up into 2 rectangles. The first rectangle starts where this cursor is. I call this my rotational offset. It starts here, and then it goes until the end. So it's going to start here, go until the end of this, and then go octet by octet until it hits the leftmost side. That means that the very first rectangle that I need to render for this offset is actually the full deal. So this is actually kind of a poor illustration. Let's say we're starting instead over here. That'll be what it would be on the next frame. Again, I start here, I go all the way to the end, and then I look at the previous octet, go that whole thing, that whole thing, until I reach here. And you'll see the result is almost everything, starting here, blah, blah, blah. What I didn't get a chance to do is the part just before the cursor. That is my second rectangle. So once I do that second rectangle, boom, it's in. So if I continue this process, it becomes a little bit more clear once my rotational offset dives into the second octet from the right. In fact, let's wait until we get a bit into the middle and let's talk about this. So if I wanted to draw the mountains with this rotational offset, so starting from this point, I need to start here, go to the end of the octet. As before, I go to the previous octet, do the whole thing, previous octet, do the whole thing, and then that's it for the first rectangle. That's it. Now you can see there's a lot more space on the right-hand side that I haven't gotten to yet. That's basically everything else. So I haven't had a chance to do this octet yet. So this octet is next. And then this octet, the part from before the offset, the part that I haven't done. So the second rectangle starts at the right side, does as many full octets as it can until it gets into the octet containing the rotational offset, and then it does that part just before it. And then that becomes the rest of it. So if I continue in this way, my rotational offset continues through this octet, and now maybe we'll do a frame where I'm in the middle of this octet. What do? We start where the rotational offset is, we do this part, we do the previous octet, and then we're done with that rectangle. And then we start on the right. So we're gonna have to do this whole octet, and then this beginning part of this octet before the rotational offset. If it was that hard to explain in English with a visual aid, imagine how much code it took in assembly to get it to work. It took a fair amount of code, including a bunch of self-modifying code to try to speed it up. But can you think of why this might be rhythmically slower? Why in some cases this would be slower and in other cases it wouldn't be? I myself wasn't sure, but I figured what if it were true that certain octets are faster to start from and certain octets are slower to start from, then I could take a look at the rot offset variable. The rot offset variable is something that the draw rotated region subroutine uses to tell it where to start the stack blasting. This is the offset. This is that cursor that you saw in the visualization. And it starts at the very beginning of the last octet, moves forward through the last octet, and then it rewinds back to the beginning of the previous octet and moves forward through that octet, and so on. This decides where the mountains start. So as this changes frame by frame, that's what simulates the scrolling, the rotation. Whenever draw rotated region is called, that rot offset needs to be initialized. And in the case of drawing the mountains and the buildings, it gets initialized with this more specific variable, this rot offset variable that tracks what's going on with the background. That gets pumped into here, which is just used by a draw rotated region, which doesn't know if it's doing the background or if it's doing the ground or potentially something else. So the idea is, can I keep my eye on the value of rot offset and try to draw a correlation between the value of this and whether the background seems to be scrolling slow or scrolling quickly at that point? If there's a consistent relationship between this value and the speed, then I know that I found the problem. I have been setting a breakpoint right here just before the sync, but now I'm going to go up a bit and set the breakpoint here. So this is right before we update the variables that rotate the mountain. That way at this point, I will have already stack blasted the mountain, and this variable that specifies where the background rotational offset is will match the stack blasting that I just did. So this is located at 412B, 412B, and this breakpoint is at 3E69. All right, I'm gonna let it go a few frames before I start looking, but you'll see this started at 18 and it's going up. 18 is 24. In fact, maybe I'll bring it back until it goes back up to hex 18 again. Oh, there it was. Okay. All right, so my beam Y at this point is 183, so that's giving me an idea of how long it took to get to this point. 183, 183, so that's pretty consistent. We just went down to 177. Now we just went up to 192. Okay, so now we're big. So once this hit about 11 or 12, we hit it big, 192, so that's low. At 8, we're at 186, but now back up to 192. So now we're at 9, A, C, so still 192. Just went down once we hit down to 1. So we're now at the 177s on these numbers. 113, back up to 183 for 19, 19, 1A, 1B, that's pretty big. Down to 177 for 10, but now back up to 192. We seem to be at the slowest parts when the rotational offset is in this region or this region. So this region is between hex 8 and F, and this region is between hex 10 and 17. Now it's possible that when we're right at the border, things go fast, but once we're inside this octet, these seem to be the slowest octets. And I think the reason is because when we're inside these octets, there's the most fix-ups, the largest number of fix-ups we have to do. When we're on the ends, so for example, when we're here, when we're on the leftmost octet, we end up with 2 rectangles as usual. The very first rectangle is tiny. All we're doing is we're starting here wherever the rotational offset is and going to the end. The second rectangle is big, but it gets to take advantage of full 8-byte octet stack blasting. So the second rectangle starts here at the rightmost octet. It blasts the full thing, blasts this next full thing, blasts this next full thing. That's a full 8 bytes of stack blasting, which is just a single pair of pulls and pushes per line. Then when it gets back to this, it has to do whatever remained, so whatever went up to that cursor. So again, when we're on the end here, it's a combination of one tiny rectangle, just from here to the end, and then the second big rectangle gets to use 3 full 8-byte stack blasts per line, plus whatever fix-up is before the rotational offset. And similarly, when we're here, it's kind of just the reverse. So the first rectangle is the big one. It's going to start here. It's going to do some variable number of bytes, but then it gets to do a full 1, 2, 3 octets, each full 8-byte stack blasting. The second rectangle is tiny, and it just covers whatever part goes up to the rotational offset and other variable bytes. So here as well, we're taking advantage of one tiny rectangle plus a large rectangle that gets to use full 8-byte stack blasts. Now compare that with one of these 2 inner octets. So for this one, the first rectangle consists of going from here to the end of this octet, and then the octets prior. So 2 8-byte stack blasts, pretty big. And then the second rectangle consists of this last octet, a full 8-byte octet, plus whatever portion before the rotational offset is that we haven't gotten to. So you'll notice it's always the same amount of bytes, obviously, that we're stack blasting every time. But think about the fix-ups. We were only able to do 2 8-byte stack blasts at a time for one rectangle, and then 1 8-byte stack blast for the other rectangle. Comparing that with when we start on the end, we get to do 3 8-byte stack blasts in a row. So my hunch at this point is that the slower frame draws, the slower stack blasts, are due to extra fix-ups that we have to do, which don't take advantage of simple, uninterrupted 8-byte stack blasts one after another. So I suspect that what we really want in order to be fast is for us to be using this block of code that very quickly can do 2 full 8-byte octets in a row. And the reason is that the code divides things up into the high group, the low group, and up to 2 middle groups. And not all group is present in any given rectangle. But for example, in one of the quick ones, if I were to start here at this rod offset, This would end up being my low group. This would end up being my middle two groups. And then this would be the high group, and it would just happen to be a full 8 bytes. But I'd be able to do these two middle groups without any fix-ups. And then presumably this third group with minimal fix-up, but there might still be some code to check. So in order to get to this position, all of the setup code needs to load X with the address of that code and store it into this jump address using self-modifying code. And so that's happening here. When we're done copying high group, then it's time to do our middle groups, and this is going to jump wherever we tell it to jump. Hopefully here, then we get a full 16 bytes of stack blasting. But if there's only one middle group, it's going to jump here and only do one. And then there are cases when there are 0 middle groups, in which case this is just going to jump here and we're going to immediately do the low group. So to test this, the question is, will the rot offset be those fast octet numbers when this line of code is run? So when we initialize ourselves to do 2 middle groups, is that indeed going to be the fast octets? So I set a breakpoint here, and then I can peek here at my rot offset to see exactly when that gets hit. And here I'm already hit at the first breakpoint, and I see we're at a 1. So I'm just going to keep skipping ahead. 2, 3, 4, 5, 6, 7, and then we skip to 18. So that's equivalent to doing 1, 2, 3, 4, 5, 6, 7, and then skipping all the way up to here to 18. And it looks like we'll probably be hitting it as we go from 18 up to 1F. So keeping our eye here, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F. And then you might have seen this skipped. This did all of the slow ones, and then we skip back to the fast one again when we're at 1, which means after we did this, we did these 2 slow dudes, and then we ended up back here again. So I think that's it. I think the extreme variability of this overly complicated but very extensible stack blasting code is due to the fact that where that rot offset cursor lives completely determines very heavily different performance characteristics. So I believe we've identified the problem, and fortunately for us, the problem is in the most complicated, long-winded code in the whole doggone project. I have an idea on what to do, but goodness gracious, if you've been with me this long, I don't think you can hold on much longer. So I'm going to give my idea a whirl, and as a preview, it will involve a lot more memory, but will hopefully significantly simplify this code so there are far fewer cases, and so that the performance is a lot more predictable. Until next time, thank you. Are you really still watching? 'Cause wow. And even if you aren't hearing me say this, or you skip to the end just to see, still thanks for watching whatever you watched, because this one was a tough one. Hopefully the next one will be much simpler, since I am planning to write simpler code. We'll see.